In this chapter, we will discuss qualitative methods for differential equations. So not finding exact solutions, but rather analyzing differential equations using various graphs. Let's start off by thinking about what are the equations that we have already studied and what are some of the complex equations that we do not have exact solutions for. So far, we have studied what are called linear differential equations of the form y prime equals ky, whose solution we found to be y equals y naught e to the power of kt. And the second solution, y prime being a minus by, whose solution was a more complicated version of the previous equation, a over b minus a over b minus y naught e to power negative bt. As I already mentioned, these two are what we call linear differential equations because on the right-hand side, in terms of y, we have a linear equation. Y only appears to the power of 1. More complex differential equations are not linear and therefore they cannot be solved using the two formulas we have just seen above. However, they describe very useful modeling situations. For example, this first equation here, where v is the velocity and g is the gravitational force, is describing how the falling object's speed changes. This next equation here, y prime equals sine of y, is also not linear because y is not to the power of 1, but rather hidden inside a trigonometric function. This describes how a pendulum works. This last equation in my examples here, h prime equals square root, so once again not linear, of h, describes how the water drains from a differently shaped containers. What we're going to do in this section is try to think of methods or develop methods that will help us analyze the equations that are not linear and therefore the ones that we cannot solve. Let's start with the first equation that we will see all the time because it has numerous applications throughout and actually reappears in different forms throughout the course. This is called a logistic growth equation. Recall, we will start with the population equation that we've already worked with. P prime, so the rate of growth of the population, is proportional to the population size, where the constant of proportionality depends on the birth rate and the death rate. Now, this is a linear model because p here appears to the power of 1. However, what we're going to do is make the model a little more complex and a little more realistic. We're going to suppose that per capita mortality rate increases with population size. You might want to think about for a second, why is that the case? Why is it true that the more, let's say, people in the population, the higher the mortality rate? And then you can think of the recent statistics we've been seeing for COVID-19. There are more deaths at higher density due to a number of reasons. For example, faster disease spread or fewer medical resources, and also fewer general resources such as food. So this is a very normal or reasonable assumption to make. So we're going to assume then that the mortality rate D, the death rate, the same one as we've seen here, is not just a constant, but rather itself is proportional to population size. Proportional means we need to introduce another proportionality constant, let's call it, for example, C, and the population size is already what has been labeled P. So our mortality rate is proportional to population size. Let's now rewrite this exact same equation, but with this as the value for D. So what we have is P prime is equal to B minus dP. That's what we've derived here, same equation. And now I'm going to plug D into this equation, our new form for D into this equation. So what we have is B minus D, which is now Cp times P. Let's open up the brackets to ensure that what we're seeing is not exactly what we've seen before. So I'm just going to open up the brackets here, and what we're going to get is BP minus CP squared. This really emphasizes the fact that we haven't seen this equation before, and we don't know its solution because it's not linear. So it's definitely not in the form y prime equals ky or y prime equals a minus by. What we're going to do next is sort of massage this a little bit. We're going to rewrite it in a form that will introduce constants that are easier to work with and have more meaningful relationship to the model. So what I'm going to do next is I'm actually going to factor out BP. In doing so, notice that my first term simply becomes 1, and my next term becomes C over B times P. It might be easier to check going the other way around. So if I open up the brackets now, I should get the exact same expression as I had before. Now this way, once I have a 1 in here, this model will be a little bit easier to analyze. But what I'm going to do is even simplify, or rather, at this point, I think it's going to look like I'm complicating it a little bit more. But what I'm going to do is actually shrink this constant to just one constant. I'm going to call it K, but I'm going to put it in the denominator. So P over K. So what I've introduced here is my value for K, which is actually B over C. And this is going to be actually carrying capacity, as we will see shortly. So simply rewriting the equation in a different way altogether introduces the value for carrying capacity, or horizontal asymptote, visible within the equation itself. So for the constants that I have, this is my K, and I also still have this constant B that I've actually always had all along. This B is the per capita birth rate, or we also call it intrinsic growth, meaning that this is just something that the population follows naturally itself. So altogether, this model is called logistic growth. Logistic growth, or also, this is one of the examples of what we call density-dependent growths. The higher the density in this particular case, the higher the mortality rate, so the model actually accounts for that. Let's now see what we can do in terms of analyzing this without having previously derived solutions at our disposal. So for the logistic growth, we're going to have to analyze the function given its derivative using these differential equations. Let's recall our Calculus 1 tools. If I have a derivative, what does it tell me about the function itself? One of the first pieces of information I can derive are, of course, the critical points. So the critical points of the function p of t are given when the derivative is either 0 or it does not exist. So let's start with our first case, when the derivative is 0. That means that my right-hand side of this equation needs to be 0. bp 1 minus p over k is equal to 0. And here we have a product of two things equals to 0, which means that either the first thing is 0 or the second thing is 0. It's not hard to figure out that the first thing being 0 only happens when p is 0. B is the intrinsic growth birth rate, so we assume that to be non-zero. In fact, we assume all of our constants to be non-zero because otherwise they will produce some very boring models. And this is 0 when p is equal to k. So notice if I plug in p is equal to k on the top here, k over k is 1, 1 minus 1 is 0. So those are my two critical points from this case. Now what about when the derivative does not exist? So I have to look at my derivative here and wonder what are the values of p I can plug in that will not produce a number, that will produce a number outside of the domain. Now this, as we've derived on the previous slide, is really just a quadratic function, which means that it's defined for all numbers. So this case will produce no solutions, which means we have two cases for the critical points. Now, the first one is kind of a given one anyway. This says that when the population is 0, then that's a critical point. Well, we know from real-life experiences that if the population is 0, then it's probably always going to stay at 0, and we're definitely not interested in any population values below 0, so I can simply start my analysis at 0. Now, the next critical point is k, so I'm going to put that on my number line somewhere. I don't know what the value for k is, but here we go. And then I can reproduce the first derivative analysis the way we have done so in Calculus 1. So what do I have on the left and on the right here? This is the number line for values of p. So on the left here, I have that these are the values of p that are less than k. What does that mean in terms of the derivative sign? Remember that what I really care about is to find out whether p prime is positive or negative, because that will tell me whether the function is increasing or decreasing. If p is less than k, what I have here in this quotient is that the top is less than the bottom, which means that, actually, let me write this down, pk, right? If the top is less than the bottom, that means that the entire quotient is less than 1. If the entire quotient here is less than 1, then I'm subtracting a number smaller than 1 from 1, which means that in the brackets here, I am going to get a positive number. So 1 minus p over k is going to be positive. If the value inside the bracket is positive, I know that b is a positive constant, p is a positive number, the whole thing is positive. So p prime here is going to be positive on this region. If the derivative is positive, recall that what that means in terms of the function is that the function is increasing. Now, similar analysis, but on the other part of the number line will produce basically an exact opposite result. So here I will have that p is bigger than k, which means that in the quotient p over k, the top is bigger than the bottom, so I'm dividing a bigger number by a smaller one, which means that the result is bigger than 1, which means that I am now subtracting a number bigger than 1 from 1, which means I'm going to get a negative result, which will in turn mean that p prime here is negative, and that will mean that p is decreasing. Okay, so in terms of Calculus 1 analysis, p is increasing, p is decreasing, something is happening at the value of k, and the value of k is in the denominator here. So for purposes of my actual function, I know that this is likely going to be a local max, but I have to think about it in terms of the derivative all along. How else can we attack this equation and also keep in mind this information? Let's think about maybe opening up the brackets and analyzing it as a quadratic equation. So let me rewrite my logistic growth equation, bp 1 minus p over k. So I'm going to open up the brackets. I'm going to get bp minus b over k, p squared. And again, I've introduced this value of k, but I've known that this was quadratic all along. Let's recall our dominating power analysis. This has a power of 1, and this term has a power of 2, which means that this term will dominate for small values of p, and this term will dominate for large values of p. Now, for large values of p, I have a squared term, and that's not something I can solve for. But let's follow through with this piece of information. What does that actually mean for small values of p? So for small values of p, that means that p prime, my derivative, will be dominated by this term. So p prime is equal to bp. This is fantastic news, because this is exactly of the form y prime equals ky, which means that this equation I can solve. So for small values of p, what I'm going to have is p equals to p naught e to power bt. It's an exponential function. I know exactly how my derivative is going to behave for small population sizes. Let's now sketch, sort of qualitatively, meaning not terribly exactly, but to give us a sense of what the graph will look like, what is the information that we actually have so far. So I have that if I start small, if my population size is small, then my function here is going to be first increasing, and then after k, it's going to be decreasing. And I also know that for small values of p, I'm going to have an exponential behavior. If I start large, so if my initial population is up here, again, based on the previous information, I know that after a certain point k, my function is going to be decreasing. And it's in fact going to be decreasing exactly after k and exactly before k. I also know that no matter what, for small values of p, so near the origin, my behavior has to be exponential. So I'm going to use here the information that I haven't actually derived yet, and that is the fact that this value for k is in fact the carrying capacity. I am providing you here with information that you're just going to have to believe me for here, and we will derive later. This is, as already mentioned, is called carrying capacity. But everything else we will get from our analysis. So my function will increase on this region, decrease on this region. And let's note that. So here I have to be decreasing 2k, and here I have to be increasing 2k. Now, I also have to keep in mind that near the origin, my behavior is exponential. So when I draw my function, I have to draw it exponentially. How does an exponential function increase? It increases in this kind of manner. So this is what the graph would look like if I start off below the carrying capacity. If I start above the carrying capacity, I have to decrease, but I have to do so in an exponential manner. So again, this is going to be like the decay graph that's going to decrease towards the actual carrying capacity. So no matter where I start above or below the carrying capacity, I have to start off exponentially. Now, this is generally a much better model for things like population growth or disease spread, because we've now introduced this notion of carrying capacity. So something has to either decrease towards it because of the lack of resources and therefore higher mortality rates, for example, or it has to increase towards it because there's still freedom in terms of growth for the population or for the spread of the infectious disease. So logistic model, being density dependent, is better than exponential model that, remember, for example, in the increasing case, assumes unbounded growth, which is simply not realistic. However, the one big shortcoming of the logistic growth is that it assumes that every population, no matter how small it starts, will eventually reach the carrying capacity. This is not true particularly for population growth of sexually reproducing species because of inbreeding and other issues. There are also populations that actually thrive at low densities and never take off in the exponential-like growth. For every population, in fact, there is a threshold below which, if the initial population P0 is below that threshold, that population will not survive. That is called a Lee effect. Look it up, it's very interesting, and it's actually just an extension of the logistic growth. The model there will start off exactly like the logistic growth, but will also acquire an extra factor, P over A minus 1. This is the Lee effect, and this makes the entire model, instead of quadratic, now cubic. So as we study models further and further, we can make the situations more realistic, but then by extension, more complex. For now, we're going to think about how we can actually produce these graphs that are accurate and not using the information that I am giving you without really proving in order to produce solution graphs that are pretty detailed. We'll first consider a couple of smaller examples on how to sketch what the differential equation is actually telling us. So let's recall that graphically, a derivative is the slope of the tangent line of the function. this is going to be instrumental in our analysis of these differential equations and any other differential equations. What we're going to do is now use this piece of information to in fact find the slopes of tangent lines to the solution and then sketch them. So here I have the differential equation of this form, y prime equals t minus 2. So let me rewrite this here just so that I can align my calculations right below it. And then I'm just going to plug in numbers to calculate the y prime values and therefore the slopes of the tangent lines for various values of t. So let's say I want to calculate y prime at 1 and maybe y prime at 2 and y prime at 3. Okay, so I'm going to plug in 1 for t. 1 minus 2 is negative 1. So I have minus 2 here, minus 1 here. I plug in 2 in for t into my differential equation. 2 minus 2 is 0. I plug in 3 for t into my differential equation. 3 minus 2 is 1. So these are the slopes of my tangent lines. Let's draw that. So here, notice that my graph is t-axis versus y-axis. I am drawing not the solution y itself, but rather the values of the slopes of the tangent lines. So when t is 1, this is t equals 1, and in fact, t is 1 all over this vertical line. When t is equal to 1, the slope of the tangent line is negative 1. Okay? And I'm going to draw myself a teeny tiny line to represent the slope. So what am I going to have? Let's say the slope of negative 1 is something like this. I know it's negative, so it's pointing down, and then I'm just approximating according to the grid lines that minus 1 will have to go through the grid lines. When t is equal to 2, the slope is 0. Slope is 0 means a horizontal line, so something like this. When t is equal to 3, so right here, the slope is equal to 1. So kind of like the opposite of my original negative 1. Now the thing to notice here is that in none of these calculations did the value of y itself ever matter. So these are going to be true no matter what y value is. And this is what allows me to extend this up a little bit. So when t is 1, whether it's for y equals 1 or for y equals 2 or for y equals 3 or for any value of y at all, when t is 1, the slope is going to be minus 1. So that means I can take this slope and extend it vertically in both directions, right? It doesn't matter what y is, so this slope will persist across all values of y for t equals 1. So let me draw in a few more just so I have them on the screen here. And it's going to be true of the exact same with the exact same reasoning for the other two. So when t is 2, no matter what y is, 1, 2, negative 1, whatever, the slope will always be 0. So that means that I can take my horizontal slope and extend it up and extend it down for all values of y. And same for 1. I can take it down and up with a slope of 1 for all values of y when t is equal to 3. Whether y is large or y is little, this is always the case. So this is great. I now have a little sketch of the slopes of my tangent lines to my equation, to my actual solution. And the last final key information that I have to remember is that solution is always tangent to these lines. Let's think about this for a second. Solution has to be tangent to all of these slope lines that I have drawn, which means that this is a very powerful graph that I've already created. If I am to place a solution curve on top of it, I have no choice. At every line that I drew, I have to be, in fact, tangent to that particular line. So going through 1, my tangent line has to have a slope that I have drawn. Going through 2, my tangent line has to be of the slope that I've drawn. And moving forward, it has to match the tangent lines that already persist. With this information and this information alone, I already get the general solution shape that the solution to this differential equation has to follow. Now, I have a general shape, but I don't actually know where it sits. It's kind of like knowing the slope of the line, but not knowing the y-intercept. It can be anywhere. It can be up or down. I know the shape, but I don't have yet enough information to fix the shape in one particular place. The initial condition gives me that information. So what I have here is that for my particular solution, I want y of 0 to be 1, which means that at 0, my solution has to sit at 1. It also tells me that t equals 0 is a point of interest, so I can actually compute the slope at t equals 0 if I want to make a more precise sketch there. I plug in 0 in for t here, and I'm going to get minus 2. Now recall that this was the slope minus 1, so at 0, I'm going to have a more steeper negative slope of negative 2. And now starting from here, again, I just have to follow the actual shape of my tangent lines in order to create the general shape of the solution. Going from there, following in the tangent lines, remembering that at every point of t, I have to follow these particular lines. This is my solution shape, y of t. With just plugging in a few numbers to calculate the slope and having the initial condition, I'm able to produce the general shape for the solution of my differential equation. This is quite a powerful technique. So what we have produced here on this graph by sketching all of these values for the slope is what is called a slope field. So again, what the slope field gives us is the general solution shape that the solution to a given differential equation has to follow. Now, because these solutions can lie anywhere, what the slope field actually gives us is what's called a family of solutions. All of these are going to be solutions to a particular differential equation. Once you have the initial condition, you get a particular solution that matches that particular initial condition. Slope field is one of the two very useful graphs that we can produce for a differential equation without actually being able to solve it. The other one is called a phase diagram. So in this example, we're going to produce both. On the left, I'm going to have the phase diagram, and on the right here, I will construct a slope field. Now notice right away the difference in axes. In the slope field here, just like the one on the previous page, I am sketching t versus y, which means that you're sketching slopes for the actual solution, and then if you can follow those slopes to produce a graph, you will be producing the graph of the actual solution, y, to the differential equation. On the phase diagram, we're going to be sketching y versus dy by dt, so y prime. So we're not sketching the solution itself, we're actually sketching the differential equation as is, where we take the y as the independent variable. You can think of that as what would normally be called x in Calculus 1. And on the y-axis, we will be sketching y prime. So let's do that first. Let's think about what does that look like if y is treated as the independent variable. If I open up the brackets here, so let's do this real quick so that it's maybe a bit more of a familiar format. Minus 1/2 times negative 4 is going to be plus 2. So here is what I have, minus 1/2 y plus 2. There's a couple of ways to sketch this. If you're comfortable thinking in terms of this is your, let's call it horizontal variable, then you will quickly recognize that this is actually a line of slope negative 1/2 and the y-intercept, the new y-intercept of 2. If you're more comfortable plugging in specific values of y, that's totally fine too. We can plug in, for example, y equals 0, which will correspond to the point on the vertical axis here. If y is 0, we get that the result is 2. If y, for example, is 2, we will get the overall value of 1. And if y is 4, we're going to get 4, and so on. Okay, so whether you recognize it as a line or you have to plug in a few points, that's totally fine. Once we see a bunch of these examples, you will get more comfortable with noting whether the overall shape is linear or some other function. So what do we have here is now a phase diagram. We're going to have to actually come up with a notation and think about this a little bit more, but let's sketch the slope field first. So notice that the shape of the differential equation here is qualitatively different from the previous one. In the previous one, on the right-hand side, I only had t involved, which means that I was able to extend my slopes for any value of y. In this particular equation, I only have y value involved, which means that my logic is going to be a little bit reversed. The method itself will not change. All I have to do is plug in numbers. So let's just do that. If I plug in y equals 0 into the differential equation here, you can do this in here or in the expanded form, it doesn't matter. If I plug in y equals 0, I'm going to get that y prime is equal to 2. If I plug in, for example, y equals 2, just to keep numbers even so that I don't get fractions, if y is equal to 2, I plug it into here, I will get that y prime is equal to 1. If I get a 4, I will notice that if I plug in 4 into here, I will get minus 2 plus 2. So overall, y prime is equal to 0. And let me plug in one more, let's say 6, for which y prime is going to be negative 1. And notice that similarly to my previous example, but for the different variable, all of these slopes depend on y only and not at all on t, which means that I should be able to extend these slopes no matter what t is. This is no matter what t is. And let's remember that as we sketch now. So what am I going to have? When y is 0, well, that's, for example, down here, y prime is equal to 2. So I have to have a slope of 2. There, for example, is a slope of 2. When y is equal to 2, so up here, if this is now my 2, the slope value has to be equal to 1. So not as steep. When y is equal to 4, the slope value is 0, so flat. And when y is equal to 6, the slope value is minus 1. So at 6, I am at negative 1 as a slope. And again, because here, this doesn't depend on t whatsoever, that means that I can extend all of these horizontally. When y is equal to 4, the slope is going to be 0 anywhere where y is equal to 4. So I'm able to extend these slopes this way. When y is equal to 6, no matter what t is, the slope is going to be 1. If y is equal to 2, I can extend the slopes that way. And for y equals to 0, same thing. Now you can sketch as many of these little lines as you want. And you can, of course, use various online calculators to actually produce slope fields for you. I find that just a few slopes will give you enough of the information to sketch the general solution shape. So let's try doing that. What if I start off with my solution down here? Again, just like in the last example, remember that I have to draw a graph that is tangent to every time it passes through or near, that is tangent to my existing slopes. So if I start down here, keeping it tangent, I will have to go this way, and then it gets less steep. And if you plug in more numbers, you notice it gets less and less steep until I hit that value at 4 and become horizontal, because my tangent suggests that that's what the curve should be. If I start up here, I will have to be tangent to this line. Again, if we plug in the value, for example, y equals 3 into the differential equation, you'll notice that the slopes get shallower and shallower as we approach this 4 of the value. If I start up here, I have to follow in the opposite direction and then again even out as I get to the value of 4. So I can sketch just one or two of the potential solution curves. And here I notice that maybe my example is a little bit more complicated than the previous one, because my solution shape now really depends on whether I start, in this case, below 4 or above it. In the previous example here, this solution shape was the same no matter where I started. I always had this parabola-looking shape. In this case, my initial condition really dictates whether the shape is going to be increasing or is going to be decreasing. So this is much more reminiscent of the logistic growth model that we've seen earlier. Now, how does the slope field connect to this phase diagram? The connection is really very deep, and we'll take a few examples and a lot of thinking to internalize. So bear with me here. What the phase diagram actually is replicating is basically this vertical axis right here. So if I think of this axis, and if I think about looking up this axis, this is going to be my best available drawing of an eye. I notice that at 4, the slope is 0, which is exactly what the value here is. The slope field produces the sketch of the slopes as the slopes. The phase diagram produces the sketch of the slopes as the actual numbers. So the height on this graph corresponds to the slope value on the slope field graph. The height here corresponds to the slope value here. And this seems to be like an easy connection, but sometimes can be really difficult to really wrap your head around. We're also, for the slope, for the phase diagram, going to think of what does that mean to be positive and what does that mean to be negative. Recall that the y-axis, the vertical axis here, is actually your y prime. So whenever you have a positive value here, that means that y prime is positive, which means that the function itself is increasing. What does that mean on the slope field? So look, between y values of 0 and 4, so between here and here, the slopes are positive. Yes, that's true. That's what we're seeing. And the function itself is increasing. Yes, that's exactly consistent. What happens on the phase diagram when we fall below the 0? So y prime is now negative, which means that the derivative is negative, which implies that the function is decreasing. And how does that correspond to what we're seeing in the slope field? For y values of 4 and above, so 4 and above, I have to have negative slopes. That's true. All of these are pointing down. And my overall shape of the solution is therefore decreasing. Yes, exactly correct. So these two things are really deeply connected and related, but they represent the same piece of information in two very different forms. Again, you can think of, and that's how the book perceives it and explains it, of this axis as being transformed into the phase diagram. What we're going to do on the phase diagram too is actually introduce arrows. And here we have to more or less come up with a convention that we're going to stay consistent with. The convention, and this is not for any particular reason, but just so that we always use the same thing, is that time moves to the right. This is also consistent with how we normally draw, for example, the time axis here. Time increases in the what we consider to be positive direction of the x-axis. Time moves to the right, and what I would like to include on this phase diagram is this increasing of the solution when y prime is positive and decreasing of the solution that when y prime is negative. This is visible on the slope field, but not yet on the phase diagram. With this convention that time moves to the right, we are going to signify the fact that y prime is positive and therefore the function is increasing by drawing the arrow to the right. We're going to indicate that y prime is negative and therefore the function is decreasing by drawing the arrow to the left. That way, let's take a look at our phase diagram. Y prime is positive means that the graph is above the x-axis, or what is called, generally calling this x-axis, I mean the horizontal axis. So y prime is positive when the graph is above the horizontal axis, which implies that I have to draw the arrow to the right. So that means on my horizontal axis, I'm going to be drawing arrows to the right when the graph is above the horizontal axis. Okay, so here I'm going to include arrows to the right. I'm drawing arrows, but really I normally just draw the actual arrowheads. There we go. So this is going to be the case when the graph is above the horizontal axis, which means that the values of y prime are positive. When the graph is below the horizontal axis, that means that the values of y prime are negative. On this region of the horizontal axis, I will be drawing arrows to the left as my convention indicates. So to the left here. There we go. And the reason behind this quick convention is that now I can see that, look, if you think of sort of just like dropping an ant on the horizontal axis here, and all the ant does is follow the arrows, then if the ant is dropped here, it will follow the arrows all the way to 4 and then stop at 4. This is equivalent to if I start on the solution below 4 here, the solution will lead me toward 4. If the ant is dropped on this side and follows the arrows, it will follow the arrows all the way to 4. So same thing here. If I start above 4, my solution will lead me down to 4. This is what also motivates the fact that 4, in this case, is called an equilibrium. This is something that the solutions converge to. Normally, slope field is a lot more time-consuming and labor-intensive to produce because you do have to produce enough slopes to be able to really indicate how your solution is going to behave. Whereas a phase diagram, because you're simply drawing the differential equation as is going to be a really straightforward sketch, and with these arrow conventions, we'll be able to tell us mostly all the same important information as the slope field would.